Oh no, there's a zombie right across this field. That's actually a bit of a problem because it can just walk straight over to me to execute its deadly mission. But what if there was an obstacle in the way? Well, now things get a bit more complicated. This is where we enter the wonderful world of pathfinding. Before I can show you how I implemented pathfinding into my custom Minecraft server I'm building from scratch in Rust, I first need to show you how Minecraft actually uses pathfinding. Contrary to popular belief, Minecraft isn't just about mining and crafting blocks. Instead, we also have things called entities. Pathfinding is an integral part of Entity AI. It's used in their wandering behavior, when chasing you down, or for villagers to find a new job site. So without pathfinding, Minecraft would be pretty boring. I mean, are you really having fun in a cave if no creepers sneak up behind you? Always finding the shortest path would be too easy. Instead, Minecraft imposes some penalties for certain kinds of blocks. These penalties also vary between different kinds of entities. Mobs will then try to avoid these blocks with high penalties, but if there is no other way, then they will still go through these. Fire, for example, has the maximum penalty, but striders don't care about it at all, so they will happily pathfind straight through it. Mobs will also try to avoid danger. Blocks that are right next to fire carry half the penalty of the fire block itself. Generally, mobs try to avoid sticky situations. Honey is also heavily penalized in the pathfinding algorithm. Then there are also blocks that a mob will never consider as a valid path. This list of blocks doesn't just contain solid blocks you can't walk through. Lava's on this list, but also water, at least for blazes. Frogs will also not step on trapdoors, and bees will never fly into cocoa. Implementing all of this will be very fun, but first we need to understand how the most popular pathfinding algorithm works in theory. As far as algorithms go, A* is surprisingly simple. You just have two sets of nodes, an open and a closed set. The open set contains all the nodes that aren't yet checked. You can think of this as our to-do list. At first, this only contains the starting position. The closed set is empty to start with. It contains all the nodes we have already looked at, so that we don't check the same node multiple times. A node contains its position and a reference to its parent. This is important so that we can retrace our steps and get the actual path to travel once we found the goal. There's also a cost, which just tells us how close this node is to the goal. Maybe the necessity of the cost isn't quite clear to you yet. Without it, the algorithm would try searching for the shortest path by looking in all directions. With this cost, we can focus the search towards the goal by first looking at nodes that are closer to it.
Hey man, what are you doing with your laptop?
Yes, I'm trying to edit this video here right now, and I've just realized that I've maybe made a bit of a mistake explaining like the cost value for the pathfinding.
Yeah.
So what I call cost the entire time should really be the F value, I think they're calling it. And then the cost is instead, well, as you can see how expensive it is to get from the start to the current node, right? So this then would also use those block-specific penalties that I've talked about earlier. And then, yeah, the F value is then just a heuristic to basically estimate the cost from the current node to the goal. And then you would take the real cost from the start to the current node plus this heuristic. That together gives then a total sort of estimated cost. And then you would take this estimated cost basically to pick the lowest node to next look at in the open set. Right. Back to the video.
What video?
Now comes the actual loop. This loop just takes the node with the lowest cost from the open set and checks it. First, we look at whether this node is the goal or not. If it is, then we are done here. If it's not, then it goes into the closed set. Now we look at the neighbors of the node. Here we have to ignore all the neighbors that are already part of the closed set. If the neighbor is already in the open set, then we can also skip it. If it's not, then we add it to the open set with the current node as its parent. Now we run this loop until we found the goal. You should set an upper bound here so that it won't run forever in case there is no path between the start and the goal. Once the goal is found, we can retrace our steps by repeatedly looking at the parent until we are back at the start. Now we have found a path between the starting point and the goal. There's also a good chance that it's fairly close to the shortest possible one, although we can't really guarantee that. Okay, now it's finally time to implement pathfinding into my server. Before we get into the weeds here, I should mention that my implementation isn't really fully done yet. Before I give it that last bit of polish you come to expect from me, I first need to fix my collision detection code to allow for things like entities smoothly sliding along walls or jumping up blocks. With this in mind, let's dive in. I already had the execute AI move towards player function in my entity AI code. This used to just apply a velocity directly towards the nearest player. Now I have added a new function that does the pathfinding towards a goal and then returns a velocity to get there using the calculated path. In here I'm working with block positions instead of entity positions. This means whole numbers instead of fractions. Up here I'm just converting the start and goal points to these block coordinates. Next I create the open and closed sets. These are just basic vectors containing a tuple with the position of the node, its cost and the position of its parent. The open set gets initialized with the starting position. Now comes that loop for examining the lowest cost node in the open set. I have arbitrarily chosen a limit of 100 iterations to keep it from running infinitely when it cannot find a path. If the open vector is empty at this point, then it's time to bail. In this case, we definitely haven't found a way to the goal. The next bit of code is concerned with finding and then retrieving the lowest cost item of the open vector. Is it the most beautiful code? No. Could I have somehow done this with an iterator? Yes. Will I fix it at some point? Maybe. If the node we currently look at has the same position as the goal, then we are done here. I'm just tracing my way back through the parents to find the actual path the algorithm found. Then we just return a velocity towards the next block the entity should travel through for reaching its goal. This is incredibly wasteful. Every tick I am running this whole path search just to arrive at the same conclusion most of the time. I should really store the path somewhere and recompute it when blocks along the path change or something. On the other hand, that's a very fancy way of saying that I should cache the path. And then I would have to deal with one of the two hardest problems in computer science: cache invalidation. Anyways, if the node we are currently looking at is not the goal, then we add it to the closed set. Next we get all its neighbors. This again is a pretty stupid botch job. Yeah, this is just me building an array that contains all the neighboring blocks. I'm going to call this a performance optimization. Now it's time to look at all those neighboring blocks. First, we check if the entity would collide with the block if it were to be there. If it would, then we can just safely ignore this neighbor. Same for if there is no solid ground underneath it. Otherwise, entities would try to pathfind straight over a canyon. The results of that would be exciting, but not desirable. Now that we have determined that the neighboring block is valid, we have to compute its cost. In my case, I'm just using the distance from the neighboring block to the goal as the cost. Last but not least, we need to add this neighbor to the open list for examination, but only if it isn't already in the closed or open set. And that's it! And now entities in my server can find their way to their goals. Well, that would be if the entity AI wasn't such an afterthought and they actually had goals to reach. Really, right now this is just used for creepers creeping up to players and animals to come towards you when you hold food. At least the bones are now there, so that I can focus on adding more entity AI stuff soon. Usually when I make one of these videos, I can announce a new release of my project, but not this time. I'm still working away on the next version 0.9. This update is by far the largest I've ever worked on, as it basically aims to make monsters do stuff. And also spawn naturally whenever conditions allow. Anyways, get subscribed if you don't want to miss videos about that. See you soonish. It's used in their wandering behavior when choosing the dog. Oh man, it's too hot here.
Stop!
Yeah, you're being secretly filmed the entire time.
Are you a creep? Get away from me!